Every time your database commits a transaction, it's making a promise. A promise that your data is safe, consistent, and permanent. But what happens when the power goes out right in the middle of that promise? Picture this. A customer places an order on your e-commerce site. The database needs to update the inventory table, insert an order record, and charge the payment. That's 3 separate writes to 3 different places on disk. Now imagine the server crashes after writing the order, but before updating the inventory. You've just sold an item you didn't deduct from stock. The data is inconsistent, and your database has broken its promise. This isn't a rare edge case. Hard drives fail, power supplies die, operating systems crash, and every single one of these events can leave your database in a corrupted, half-written state. So how do databases actually survive this? The answer is something called write-ahead logging. To understand the problem, you need to know how databases store data. Everything lives in pages, typically 8 kilobytes each. A single table might span thousands of pages scattered across the disk. When a transaction modifies data, it needs to update specific pages. But here's the critical issue. A single transaction often touches multiple pages that are physically far apart on disk. Updating them requires random I/O, jumping from one location to another. And here's the fundamental problem. There is no way to atomically write to multiple disk pages at once. The operating system writes one page at a time. If a crash happens between page writes, some pages have the new data and others still have the old data. Even a single page write isn't truly safe. If power fails mid-write, you can end up with a torn page, where half the page has new data and the other half has old data. What we need is a way to make multi-page updates atomic, and that's exactly what write-ahead logging provides. Here's the elegant solution. Before you change any data page, first write down what you're about to do in a separate log file. This is the write-ahead log, or WAL. Think of it like a pilot's flight plan. Before takeoff, you document every step of the journey. If something goes wrong mid-flight, anyone can look at the plan and figure out exactly where you were and what needs to happen next. The golden rule of WAL is simple. The log record describing a change must be written to disk before the actual data page is modified. Log first, then change the data. Never the other way around. Why does this work? Because if the system crashes at any point, the log tells us everything. If the log says a change was committed but the data page wasn't updated yet, we can redo the change. If the log shows an incomplete transaction, we can undo it. The log becomes our single source of truth. No matter when a crash happens, we can always recover to a consistent state. So what's actually inside a WAL record? Let's break one open. Every record starts with a log sequence number, or LSN. This is a monotonically increasing identifier that gives every log entry a unique position. LSN 100 always comes before LSN 200. This total ordering is essential for recovery. Next is the transaction ID. This tells us which transaction created this record. Then the page ID and offset, which identify exactly where on disk this change applies. The most important fields are the before image and after image. The before image is the old value that was on the page. The after image is the new value being written. Having both means we can go forward by applying the after image or go backward by restoring the before image. Finally, there's a previous LSN pointer that links to the last record written by the same transaction. This creates a chain we can follow to find all changes made by a single transaction. Together, these fields give us everything we need to redo or undo any change. Let's trace a transaction from start to finish and see where WAL fits in. When your application issues an update statement, the database first loads the relevant data page into the buffer pool. That's a region of RAM where the database caches frequently used pages. The page gets modified in memory, and a WAL record is created in the WAL buffer, also in memory. At this point, nothing has been written to disk yet. Everything is in RAM. Now the transaction commits. This is the critical moment. The database calls fsync to flush the WAL buffer to disk. This is a hard guarantee. The operating system forces every buffered log record onto the physical disk. Once fsync returns, the transaction is durable. But notice something interesting. The actual data page is still only in memory. It hasn't been written to disk yet, and that's perfectly fine. The WAL record on disk contains the afterimage, so if we crash right now, recovery can reconstruct the data page from the log. The dirty data page will eventually be written to disk during a process called a checkpoint. If dirty pages just sit in memory, the WAL file would grow forever. And during recovery, we'd have to replay the entire log from the very beginning. That's where checkpoints come in. A checkpoint is like saving your progress in a video game. Periodically, the database pauses, flushes all dirty pages from the buffer pool to disk, and writes a special checkpoint record to the WAL. This checkpoint record says, at this point in time, all data pages on disk are up to date with every log record up to this LSN. So during recovery, we only need to replay log records after the last checkpoint. Everything before that is already safely on disk. The trade-off is straightforward. More frequent checkpoints mean shorter recovery time after a crash because there are fewer log records to replay. But each checkpoint causes a burst of disk I/O as dirty pages get flushed, which temporarily slows down normal operations. Most databases let you tune the checkpoint interval. PostgreSQL defaults to 5 minutes or when the WAL reaches a certain size, whichever comes first. When a database restarts after a crash, it runs a recovery algorithm. The most influential one is ARIES, and it works in 3 phases. Phase 1 is analysis. The database scans the log forward from the last checkpoint. It builds 2 lists, the set of transactions that were active at crash time and the set of pages that might have unflushed changes. This tells recovery exactly what needs attention. Phase 2 is redo. This is the counterintuitive part. The database replays every logged change from the checkpoint forward, even changes from transactions that will ultimately be rolled back. Why? Because redo restores the database to the exact state it was in at the moment of the crash. We need that precise state before we can safely undo anything. Phase 3 is undo. Now the database walks backward through the log, rolling back every transaction that never committed. It uses the before images to restore the original values. Each undo operation itself gets logged, so that if we crash again during recovery, we can continue from where we left off. After all 3 phases, the database is consistent and ready for new transactions. Here's what makes write-ahead logging truly elegant. A single mechanism provides 2 fundamental ACID guarantees at once. First, durability. When a transaction commits, its WAL records are flushed to disk. Even if the server crashes 1 millisecond later, those records survive. During recovery, the redo phase replays them, ensuring every committed change is permanently applied. Your data is safe. Second, atomicity. If a transaction was in progress but hadn't committed when the crash happened, its WAL records show it as incomplete. During recovery, the undo phase rolls back every change from that transaction using the before images. It's as if the transaction never started, all or nothing. The same log records serve both purposes. The afterimages enable redo for durability. The before images enable undo for atomicity. 2 guarantees from one elegant mechanism. This is why virtually every serious database system implements some form of write-ahead logging. It's not just a good idea. It's the foundation that makes reliable databases possible. Write-ahead logging isn't just a safety mechanism. It's actually a performance optimization. Remember, without WAL, the database would need to write every modified data page directly to disk at commit time. Those pages are scattered all over the disk, requiring random I/O. The disk head has to seek to each page location, and seeking is slow. WAL changes the game completely. Instead of writing to scattered pages, we append to a single sequential log file. Sequential writes are dramatically faster than random writes. On spinning hard drives, the difference can be 100 times. Even on modern SSDs, sequential writes are 10 to 50 times faster. There's another trick: group commit. When multiple transactions are ready to commit at the same time, the database can batch their WAL records together and flush them with a single fsync call. This spreads the cost of one expensive disk operation across dozens or even hundreds of transactions. So WAL gives us crash safety and better performance. That's a rare engineering win where the safe choice is also the fast choice. Write-ahead logging isn't just a textbook concept. It's running in every major database you use today. PostgreSQL stores its WAL in a directory called PG_WAL. Every change to every table goes through the WAL first. PostgreSQL also uses WAL for replication, streaming log records to replica servers to keep them in sync. MySQL's InnoDB storage engine calls it the redo log. It uses a fixed-size circular buffer of log files. When the buffer fills up, InnoDB forces a checkpoint to make space. The same redo log powers InnoDB's crash recovery. SQLite has a WAL mode that you can enable as an alternative to its default rollback journal. In WAL mode, readers never block writers and writers never block readers, making it perfect for applications with concurrent access. The details differ, but the core principle is always the same. Write the plan before doing the work. Log first, data second. And when things go wrong, the log tells you exactly how to recover. Next time your database survives a crash without losing a single committed transaction, you'll know the secret: write-ahead logging.